Welcome back to ECE 501B. This is the next to the last lecture. We have one more lecture on Wednesday, and that's when your project assignment is due, the deliverable number 2 and deliverable number 3. Number 3 is the reflective paragraph. And sometimes people forget to do that, so I've been trying to make it very clear that you have 3 deliverables for your project, 1, 2, and 3, and 1 has already happened. Yes? You may include number 3 with number 2. You can put it all in one package. That's fine. And you can submit that. I think there's a drop box, is there not, for deliverable 2? Is there a separate one for 3? Is there? So if there is, you don't have to separate them. I just need to have both of them somewhere. Okay, so if it's easier for you to include deliverable 2 and your report and your reflective paragraph in one document, that's fine. I will find them. It's just if you don't include 3, I can't find it. But if you include it in a separate Dropbox, if that's what I've created, that's okay also. But you don't have to. Just make sure that I receive both deliverables by Wednesday evening. I think that's 11:59 if that's the standard time. And tonight, your homework number 8 is due. Teacher course evaluations are also due. The response rate is not overwhelming, but it's above 50%. So that's maybe better than my other class, but not much better. So I would like to get it pushed up. So if you know people that aren't here, I'm guessing I'm probably speaking to those that maybe have submitted the TCE. So if you nudge your virtual classmate to submit that, my other class is wanting extra credit, and I said, yes, if we get it up to 100% participation. Then it probably won't happen. Yes? What exactly do you have to write in the reflective paragraph? I don't remember, but basically commenting on your project experience. What did you get out of it? What seemed to make you maybe a little bit more aware of some of the material that we've been talking about in class? Or now did it make some of this material stand out or more meaningful to you after trying to digest something new, a project paper or something that you're doing for your project? What I would like for you to do is say, and I would read the description. It asks what it states what the reflective paragraph should contain. So basically it's reporting on your experience. What did you like about it? What did you not like? Would you think that some of the material that you had in your project should be included in the course, actually? And it's not necessary to be a 4-page paragraph, okay? It needs to be 4 or 5 well thought out sentences, maybe, in terms of your reflective paragraph. And I hope that I've included some hints as to what to include in your reflective paragraph. The final exam is a week from tomorrow. It's a Tuesday. It's not a Monday or a Wednesday. And the final exam will be, I really don't want to say this, but it's up until today in terms of material. So don't check out is what I'm saying for the next 2 lectures, but you won't really be held responsible for the infinite dimensional material that we will cover today and Wednesday in class. But everything up until that point, it is comprehensive, and for that reason, basically, it's the Axler textbook and the material that we've covered from that. Yes, this comment, maybe it wasn't a question, but the comment from the audience or from class was, is it difficult to write a question in infinite dimension? I don't know that I want to go that far into the question. No, I think it could be easy to write questions, but we just haven't had a chance to give and take that material, and so you haven't had that much time to digest the material either. So what I want you to do now is sort of sit back and try to reflect on what you have seen in the finite dimensions and see how that now relates to what I'm suggesting it relates to in infinite dimensions. That's the idea. But the final exam, I'll talk, I guess, a little bit more about that as far as the process. Wednesday, there is a review session posted online with notes and video from an earlier semester, but I believe now you get 4 pages of notes, front and back. If you need them, you don't have to have 4 pages of notes, and it's a 2-hour exam. But structurally, it should look similar to the previous midterms, types of problems, etc. Today, what I'm wanting to do is get started with the second half of the class, which is the second textbook, which is Signal Theory by Franks, and that's really a subset of functional analysis. So if you hear somebody talking about functional analysis, you can start to better understand or appreciate what they're talking about or referring to based on the material that we're going to cover. We'll look at a motivational example, which is convolution. We'll see that convolution is a linear operator. And in fact, what falls out is this Fourier expansion. We'll see that instead of eigenvectors, now we're talking about eigenfunctions. So functions are now infinite dimensional, whereas vectors have been held to a finite number of components or coordinates in those tall, thin objects that we've called vectors. And we already know that vectors don't have to necessarily hold to that structure, but sometimes that gives us a nice way of thinking about finite dimensional vectors. Then we will talk about signal sets, and once we have some examples from signal sets, we'll talk about set partition and equivalence, and then we'll go from there in terms of what we can do or what you can actually say relative to infinite dimensional vector spaces, and we'll start talking about Banach spaces, or at least we'll define those. We'll define Hilbert spaces, etc. And those are related to what we've already learned in the sense of normed linear vector spaces in finite dimensions and inner product spaces. So that's sort of how Banach spaces and Hilbert spaces overlap or correlate with the finite dimensional material that we've already discussed. Now, whenever you hear signal theory, you might start to think vector, and you might make this connection between a signal and a vector in the sense of signals carry information just like a vector can carry information. The information in a vector, its components or coordinates, tell us something about that vector. Now we might have a signal, and now we need to know what kind of information can be contained in or found in that particular object. And we want to start talking about how signals can be classified, and if you've taken earlier signal classes, signal and system classes as an undergrad or a graduate, you might have had to classify signals as energy signals or power signals, and how do you represent those? And this signal space notion from Franks, or this signal space viewpoint, allows us to start thinking about signals geometrically. Just like we have the coordinates in a vector, maybe giving us this 3-dimensional image, and then we extended it to higher dimensions, now we have signals, and how can we sort of think about these signals as different functions that might be orthogonal, orthonormal, and we can start to do the nice things that those kinds of functions do, similarly to how we can combine or add up combinations, linear combinations of orthonormal vectors that we've talked about in finite dimensions. With respect to the textbook, the second textbook, chapters 1 through 5 are foundational. That's today. Wednesday is chapter 6 through 10. No, we're not going to get that far. But that's sort of the outline of the second textbook, which you can find in the resource section or course resources section on D2L. Ideally, we would cover all of that, but that's probably not going to happen. But we will try to lay the foundation today. And what we're trying to do is connect our previous finite dimensional space information with infinite dimensional signals. So now, whenever we talk signals, maybe think vectors or make that connection so that you can start to better appreciate what's going on or being discussed when we are dealing with signals. So let's try to introduce this and motivate this signal space idea in the second textbook. So let's start by considering a list. And here I'm saying X is now going to represent well, let me not make it infinite dimensional. Let me say that it now terminates after some finite collection of coordinates. And suppose that we plot those values, meaning let's just try to say our index is the independent variable, and now at index 1, 2, 3, let's say up to 8, maybe now we have something that maybe I should have just gone up to 8. Let me go ahead and go on up to 8. And maybe you now have those particular values for X in terms of their numerical value relative to each index. And in this case, let's say little n is equal to 8. And we have 8 such values. We could now say, well, let's actually resolve that information on a finer grid so that now maybe instead of going from 1 to 8, maybe we go from 1 to 16. And now maybe we are looking at something, and don't hold me to this accuracy, but you get the idea. Now we're including more points. This now might represent x sub I with n equal to 16. And as we let n get bigger, we start to make the separation between these coordinates smaller and smaller until in the limit they're right on top of each other. So that as n goes to infinity, then this x starts to look like a function. And now maybe we have this x that goes up and then maybe comes down and does something like that. Here, now as n goes to infinity, this index I now becomes this continuous time variable t, And x sub I, instead of these coordinates, now x sub I just goes to this continuous variable or function x. And now, since we have an infinite number of points between in this segment, we can now think of this infinite dimensional vector space may be given other names. An infinite dimensional vector space, often called a signal space, or a function space. And that's one way of starting to see how we can transition from these finite vectors of coordinates into functions, and now we have an infinite dimensional vector space. Once we have these functions, we can talk about adding functions or scaling those functions. We can do these linear operations by imposing linearity with the standard definitions of addition and scalar multiplication. Now we have these infinite dimensional objects, which are functions, that can be added and scaled by scalar multiplication, which allows many of our earlier results from the finite dimensional case, many results from finite case, apply directly in this infinite dimensional setting now. And let's then see what this connection might be by an example. Let's look at a motivational example. Which is going to involve linear operators and eigenvectors and our vector representations in terms of eigenvectors. So let's remember what we know already about eigenvalues and eigenvectors. If I now ask you to, what's maybe the first thing that you think about when I say eigenvalues and eigenvectors, what do you start to have come to mind? If I say eigenvalues and eigenvectors, what might you start thinking? Okay, you might be thinking about this defining relationship between an operator, vectors, and eigenvalues. So we might then recall the eigenvector equation, which then says this T v sub I is equal to lambda sub I v sub I. V sub I is this finite dimensional vector, lambda sub I is the scaling. This says now that we have a linear operator. The operator says we're going from one space back into the space, and when we operate on a particular direction, we actually are just scaling in that same direction, V sub I. If we choose the vectors to be eigenvectors. Let's now consider what that might look like if we now, instead of have eigenvectors, we have eigenfunctions. Now consider what this eigenvector equation might look like if we, instead of having eigenvectors, we have eigenfunctions. Now consider what this would look like for now what we will call eigenfunctions. Now we have t. We can still use t, but now let's use a function, we'll call it u sub I, of t, and that's now, and those t's are different. If you're listening to this, it's going to maybe get confusing. That was a capital T as a linear operator, and that was a lowercase t for the argument of this function. But now we're saying that linear operator applied to this eigenfunction really just scales that eigenfunction by some scalar amount, lambda sub I. Or this capital T, the linear operator, u sub I is, let's say, the ith eigenfunction, and lambda sub I is the ith eigenvalue. And what we want to see is how this might arise, or what this might look like when we're dealing with functions. Let's consider an operator you're already familiar with. For example, let's look at a linear time invariant system, and the operator or the concept is convolution. In this case, let's say that we now have y of t, that's the output function, is now equal to this integral from, let's say, tau equal minus infinity to infinity of x of t minus tau, h of tau, d tau. And what we want to show is that that could actually be just thought of as a linear operator applied to our input x of t. And you could make the connection maybe with what you've already learned in previous classes relative to this convolution operation. You might think of this as a way of relating an input signal x of t to an output signal y of t through this impulse response or impulse response function associated with some system, h of t. Back here, if we looked at what we've written in black, that t, if you think about this as just the leftmost side and the rightmost side, this t is actually taking a signal and mapping back into a similar signal, meaning it's maybe mapping the real numbers into real values. Maybe x is a voltage and y is something else. Maybe it's a current, but they are both consistent in terms of these are real functions. They could even be complex, but we probably won't go there. But t is an operator because both x of t and y of t are in the same space. Now, we want to see, why can we say that maybe y is equal to a linear operator on x by the fact that we have this convolution operator in the time domain? Or if we apply an input x to a system, if we know the system's impulse response, you could calculate the output. Now, how do we think of that relative to what we've learned already in terms of eigenvalues and eigenvectors? Can we think about eigenfunctions and their representative spectral information, which is what these eigenvalues are in our finite dimensional case? Let's make a claim. Suppose that we claim that e to the I omega t is an eigenfunction of our linear operator. So that's what we want to see if we can actually conclude. Let's run a check. Let's go ahead and let our input x of t be this complex exponential function, e to the I omega t. And what is e to the I omega t? When I first start teaching circuits or signals and systems, and we start throwing around these complex exponentials, students are going, oh, complex exponential, what do I even think? And I would just say, fix an omega, and now what do you really have? Now you have these rotating phasors, and you could just think of, now I have a combination of sines and cosines at a particular frequency, omega. So now if we say x of t is e to the I omega t, just remember Euler. Euler now says you have cosine omega t plus I sine omega t. And that's now your input. Your input is this complex combination of cosine and sine, and you want to know how is that, or how does the system respond to that particular set or that complex combination of sine and cosine. If we assume this, and a lot of times why do we collect these sines and cosines into a complex exponential? It's because doing integrals with sines and cosines are not very nice, and integrals of exponentials are a little easier. Usually doing math with exponentials is much easier than doing math with sines and cosines. So now we've compacted a lot of information into this I omega t, but when you see this, I would just think, oh, cosine and sine at omega. That's now what we're shaking the system with. Let's now put that into our expression, which was relating the input to the output by means of the system's impulse response. So we now have y of t is this integral from tau equal minus infinity to infinity of e to the I, and now we have x of t minus tau, which says that if x of t is e to the I omega t, then e to the I, or x of t minus tau is e to the I omega t minus tau, h of tau d tau. But our variable of integration is tau. And we actually have two exponentials in there. If we use our knowledge of exponentials, we have an e to the I omega t, and we have an e to the minus I omega tau. And the complex exponential that's a function of t can be slid outside that integral because it's not a function of tau. And that's what we are going to do. Let's now say that this is going to be rewritten. We will keep, obviously, we have to, the functions of tau in the inside the integral. We have e to the minus I omega tau, h of tau d tau, but that now can be multiplied by this second piece, e to the I omega t. But what was e to the I omega t? That was x. That was our input. And what's in square brackets? So this is actually this piece right here. This function is now our eigenfunction. If you perform this integration with respect to tau, what's going to happen? What are you going to get? Let's say you fixed omega at 10 radians per second. Now you have e to the minus I 10 tau scaling or weighting your impulse function, h of tau. What's the result of that? What will you get if you now integrate a function, e to the minus I omega tau? We can keep it as a variable of omega, h of tau d tau, and we're integrating with respect to tau. We're just going to get a number, aren't we? A constant. It could be a complex scalar, but it will just be a scalar. This is now a scalar, and let's say that we keep omega variable, so it's a function of omega, but if you plug in a particular value of frequency or a particular value of omega, you will get some complex scalar, which now says that, oh, now if I said t e to the I omega tau, where t is the convolution operator, we could write that as this lambda of omega. That's this scalar. That's that guy right there, times, or weighting, this spinning phasor. And that's what we were wanting. We were wanting our result to just be lambda of omega e to the I omega t. That's now this eigenvalue, eigenfunction relationship coming out of an operator, a linear operator. And what is this scalar? If we simply show what it's equal to in that bracketed expression right above, that starts to look familiar to us maybe. You've maybe seen this before. Lambda of omega is this integral from tau equal minus infinity to infinity of e to the minus I omega tau, h of tau, d tau, and you might think of that as now just this h of omega. It's similar to an inner product, actually. It's a function times a function's complex conjugate. And we've looked at maybe some inner products that are similar to that. And what we're saying now is, how does this lambda of omega, if you fix omega, what are you going to get? You're going to get some complex number, capital H of omega. And a complex number you can think of in terms of polar form, so that you now have a magnitude and an angle. And that's now how you will be shaping the input x, or the eigenfunction e to the I omega t for a fixed omega. Now you apply a fixed omega to your system, and this integral relationship tells us how that system is going to respond at that particular omega. But this is, omega is infinite in extent. It's from DC, 0, all the way up to infinity. So instead of having a finite number of eigenvalues, now you have this eigenvalue sort of spectrum, or this infinite number. If you picked a discrete collection of omegas, now you would have these different sort of eigenvalues, but in general, we now have this infinite, or this function, h of omega, that depends on omega for an infinite number of omegas. Or you could now say that we're looking at t applied to e to the I omega t is now going to be h of omega e to the I omega t. And what we now have seen is, instead of worrying about a finite number of eigenvalues, now we have an infinite number of complex values contained in this function, capital H of omega, or this lambda of omega. And that's because we've now moved, or we've been moving to this continuous eigenfunction relationship. Moving to continuous caused those indices sub I on x to become continuous as well. So that now, instead of having just a finite number of lambdas, now we have this function of lambdas, in a sense. Where our eigenfunctions are indexed by a continuous parameter omega. And now I'm starting to see maybe a little bit of a confusion here. Maybe I should have used J, because I used I for my index, and now I'm using I for square root of minus 1. Hopefully that's not confusing you. So I is overloaded, meaning I'm using it for many different things. In the very beginning, maybe I'm making it more confusing by reminding you of what I did. Here I said x sub I, but that was now the index on these coordinates of x. That's not what I'm using I for now. I now is this square root of minus 1, and it's these rotating phasors. So that now we can think about having this relationship in a block diagram form. Here's our linear time invariant system. We apply to that some rotating phasor, e to the I complex exponential, e to the I omega t. This is now u omega of t. And now we have learned that we can say the output is now h of omega e to the I omega t, and that you could also think of as some scalar weighting on our eigenfunction, which is just u of omega t. And I hope it's clear what I want for an answer then to this question. How many eigenfunctions, how many e to the I omega t's do we have for an infinite dimensional operator? Now I'm saying how many e to the I omega t's do we have? An infinite number. However many omegas we have, and that's an infinite number, we have a continuous number of those. So we have now this infinite number of eigenfunctions, an eigenfunction for each omega that you could think of, each frequency that you might want to excite this linear time invariant system with. And how do you now think of this? Think of this in sort of a steady state. If I now walk up, and apparently I'm known for shaking tables, but if you start shaking this table at a given frequency, or you start shaking a circuit at a given frequency, what's going to happen throughout that circuit? What kind of signal will you see superimposed on all of your different components in this electric circuit if you are applying a cosine of omega, cosine omega t? You're now exciting that circuit with cosine omega t. After all the transients have disappeared, what are you going to see throughout that circuit? And I just keep shaking at that frequency. We're not going to see any other frequencies. We will just see that frequency distributed around our system. And how will it be amplified or modified? How will it be scaled and maybe delayed in time is given by these eigenvalues, h of omega. That's a complex number which gives us a magnitude and an angle. And that tells us how, when we apply a particular cosine of a certain frequency, that system responds. And that's what's contained in this h of omega. And we now essentially use that to define what we say is this transfer function associated with any given system. So we can interpret the transfer function h of omega as the eigenvalue spectrum of this linear operator t. Because at each omega we can evaluate h of omega. For a fixed omega, capital H of omega will just give us a complex number. And that has a magnitude and angle which will tell us how the system behaves. And so that's the scaling that is going on at a given frequency. And that's now consistent with this eigenvalue-eigenvector relationship that we had in finite dimensions. And what was a nice reason for finding these eigenvectors, especially for specific kinds of linear operators? If they were self-adjoint, what happened to your eigenvectors? They were orthogonal, and if we applied a inner product or a norming to that, we could normalize those orthogonal eigenvectors to actually get orthonormal eigenvectors. And once we have a complete set of eigenvectors, orthonormal, then we can represent any vector in that vector space as a linear combination of those eigenvectors. And that's our basis. So let's now recall that. Recall the importance of eigenvector decomposition for analyzing operators on finite dimensional vector spaces. If you had a basis, let's say it's E sub I, and again I'm overusing the I. The I now is an index. You could write any vector in that vector space, let's call it V, in terms of those eigenvectors. We could say, oh, that's some weighting of our eigenvectors, and the weightings we will just say are the A sub i's. Meaning any arbitrary vector, let's say V, can be written in terms of the eigenvector basis. So that now if we have any vector that we want, now we can basically say how the operator will respond to that vector. Meaning, if we now apply our linear operator to a generic or an arbitrary vector V, the beauty of now decomposing V into these eigenvectors is because those eigenvectors are eigenvectors of that linear operator T. And in those directions, we simply scale in those eigenvector directions. Meaning TV now is T operating on this linear combination of eigenvectors where the eigenvectors are scaled, but the scalars can slide outside that operator, and now we have a sum, or sum of A sub I operating on T E sub I, but what happens to T E sub I? Since those are eigenvectors, it just scales in those eigenvector directions, so that this now becomes a summation of A sub I, lambda sub I, E sub I. And that's a little easier to start thinking about. This is a very simple process results from using eigenvectors as our basis. Now, do you remember how we found the A sub i's in this decomposition of an arbitrary vector V in terms of our basis vectors? And in this case, our basis vectors are orthonormal in their eigenvectors. If I give you an arbitrary vector V, how are you going to find the A's? The A sub i's. If I do this on the final, which I could very easily do. If I now give you an arbitrary vector V and I say decompose it in terms of this set of orthonormal vectors, which is a basis, how do you find the scalings? Well, our vectors are all, that's close. I mean, you're right there, but now I've already given you the vectors that are orthonormal. So now you want to do this decomposition using the inner product. You want to find how is this vector aligned with each of these eigenvectors. Now you're looking at the inner product of the vector v with each of these vectors, e sub I. So you've moved beyond Gram-Schmidt. You may have used Gram-Schmidt to find your orthonormal basis vectors, but now you're wanting to find, how do I find the weightings of this vector, or what are the weightings that will create this vector v in terms of a linear combination of this orthonormal basis? Meaning now, let me ask, which I already have, so let me just write it down. And how did we get the a sub i's in this decomposition of v in terms of these orthonormal vectors? So now we were essentially saying, how's v aligned with the e's, or can we project v onto each of these e's? I guess if we wanted one word, we would say projection. That's how we found these a sub i's, meaning each of these a sub i's is just the vector v inner product with the basis e sub I. That's what happened in the finite dimensional case. What happens when we go to the continuous case? Instead of now having these vectors e sub I, we have eigenfunctions. What happens in the continuous case? So that now we say, remember what the a's might be. The a's might be these, well, let me just do it. So now we have a sub I is, let's say, the inner product of an input, x of t, with our eigenfunctions, u of omega, where let's just go ahead and write those eigenfunctions as these complex exponentials. So we're assuming our input, x of t, is made up of a linear combination of these eigenfunctions. And this, a of omega, is really now the amount of our input, x of t, aligned with the eigenfunction, u of omega. That's a particular eigenfunction, u of omega. We've fixed omega. Let's recall how we can define an inner product. Meaning if I have two functions, a of t and b of t, maybe a of t is a bad choice, but we could now say that that's now this integral, from minus infinity to infinity of the first slot function and the complex conjugate of the second slot function. That's one way that we could define an inner product of functions. In the first slot and the second slot, we have a function in the first slot, function in the second slot. We now want to boil that down to a number, a scalar. That's what we want for an inner product. So, what does that give us for A of omega? If we're taking the inner product of an input signal, an arbitrary input signal x, with this eigenfunction u of omega, we now are looking at A of t, that's just the first slot, that's x of t, and what was in the second slot? That was e of I of omega t. What's the conjugate, complex conjugate of that? So that now we've found the weighting of x in the direction of this eigenfunction that's this cosine or sine. How is x aligned with this sinusoid? And x of t now can be written as a linear combination of these a's. And x of t, remember, a's are just the scaling of x in the direction of that eigenfunction. And x of t can be written as weighted sums. The weightings are these a of w's, or a sub w's, and those are applied to the eigenfunctions u of omega. If that's the case, then we're saying that, remember, well, I'll do it in just a minute. V was equal to the sum of A sub I, E sub i's. Now our E sub i's are the e to the I omega t's. These are the eigenfunctions, and our A's are these particular scalars that come from this integral. Maybe I should put the limits here. We were going from t equal minus infinity to infinity. But now x of t is a continuous waveform, and so instead of a finite sum, that sum converts into an integral. So we're now integrating over all omegas, that's the a of omega, e to the I omega t d omega. That was an integral because we were continuous. Where the finite dimensional case, let me just put that in parentheses, we had v, this vector, an arbitrary vector. Here our arbitrary function is x. In the finite dimensional case, we had an arbitrary vector v, which was this sum from I equal 1 to n, a sub I, e sub I. Now what we have is we have a way of rewriting x. We've now decomposed an arbitrary signal, input x, into a weighted sum of eigenfunctions. where the eigenfunctions are the e to the I omega t, these spinning phasors, which is consistent with this finite sum or finite dimensional case. The a sub i's are now the a sub omegas. But what are those a of omegas? That's what we've been calling this Fourier transform of little x of t, maybe in earlier classes. So we could say capital X of omega is now this little a of omega, which is this integral from t equal minus infinity to infinity of x of t complex conjugate, whoops, now I'm reverting back to I being j. Let's keep it as I so that we e to the I omega t dt. If you fix omega, the frequency, what are you saying? You're saying, how does this x of t function, how does it align with this cosine and sine at the frequency omega? That's really what this is. This is like an inner product, and we're now saying for each omega, how does x align with that frequency of sine and cosine? That's all being communicated through this integral, giving us this capital X of omega. So that the coefficients, what happened to my t? That looks like a plus sign. So that's now t. The coefficients of x of t in the omega basis. Where the coefficients are really the weightings of x of t. And if we wanted the coefficients or x of t, little x of t, we could think of those as the coefficients of this signal x in the t basis, meaning x of t we could write as this integral from omega equal minus infinity to infinity of capital X of omega e to the I omega t d omega, where this capital X of omega is really what we were saying was the a of omega before. So now a of omega are the weightings, and to find those a of omegas, we just need to compute basically how x, this arbitrary function, aligns with these various sines and cosines, or this complex exponential e to the I omega t, which we're now writing as its conjugate in this integral expression. And that's what little x of t is. All of this now allows us to make this connection between the time domain and the frequency domain. Meaning, if we now looked at this convolution to obtain the output y of t in terms of the input, x of t minus tau, h of tau is the impulse response d tau, this is now a convolution in the time domain. How does that correspond to capital X of omega and maybe our system H of omega? that now should be equal to this weight, or this expression of y of t in terms of omega coefficients, or omega weighting, meaning this is now equal to the integral from omega equal minus infinity to infinity of x of omega h of omega e to the I omega t d omega, where this is now the weighting of those eigenfunctions e to the I omega t for the output y of t. And this capital Y of omega can be found from a multiplication. So that this convolution in t is related to, or corresponds to, multiplication in omega. Now I'm writing that down, but let's just derive that relationship. Now that we know how to express x of omega, h of omega, etc., in terms of these spinning phasors. So let's derive this relationship, but this should be something that you're okay with, because how did we rewrite x of t? We rewrote x of t as some weighting of these cosines and sines, this complex exponential, e to the I omega t, which are just sines and cosines of omega. Now if you replaced x's with y's, you would get y of t as this integral of capital Y of omega, e to the I omega t, and that's what we have on the right-hand side. Except now, y of omega, by association with what's multiplying or scaling e to the I omega t, is this product of h of omega with x of omega. So that multiplication in the frequency domain is corresponding to convolution in the time domain. Let's derive that relationship. We start with y of t. That's this integral from tau equal minus infinity to infinity, x of t minus tau, h of tau, d tau. But we can write that h of tau as this decomposition of rotating phasors, meaning this is now this integral from omega equal minus infinity to infinity of h of omega e to the I omega tau d omega. That's just rewriting h of tau in terms of its eigenfunction expansion, where h of omega are the eigenvalues. E to the I omega tau are the eigenfunctions. Now we have two integrals, two variables of integration, omega and tau. Let's just slide those around so that now we have this. Let's say the first integral is integrating from omega equal minus infinity to infinity. The second integral is tau equal minus infinity to infinity. And we have x of t minus tau, h of omega, e to the I omega tau, d tau, d omega. Now we go back to calculus. let's just make some substitutions. Suppose we try to simplify this by saying, let's let the argument on our little x be sigma. Then if I look at the differential of sigma, and t is fixed, tau is our variable, what is d sigma? That's just minus d tau. And if we solve for tau, tau is now in terms of t and sigma, that's t minus sigma. Let's now use that to try to clean up this double integral. We're still integrating from omega equal minus infinity to infinity. Now, though, we're replacing tau with sigma, so that now when tau is minus infinity, what is sigma? That's infinity, so that the upper limit is now minus infinity. We have x of sigma, h of omega, e to the I omega, and now tau is t minus sigma, minus d sigma for d tau, dw. But we can now clean this up a little bit. We can say omega from minus infinity to infinity. In here we now have this integral from sigma equal minus infinity to infinity, and we'll take that minus sign from in front of d sigma to change the limits. Just flip the limits on our integral. We now have x of sigma, e to the minus I omega sigma, d sigma, and then we have left over in the other h of omega, e to the I omega t, d omega. And this inner bracket should look like what we had been using to identify the weightings of, or basically the decomposition of our arbitrary input x in terms of these rotating phasors. So that's now capital X of omega, so that we have derived this relationship that shows that we have capital X of omega times h of omega weighting or forming the coefficients or the weights on these complex exponentials, e to the I omega t, d omega, where we could now associate this product with y of omega. And this is now the eigenvalue spectrum of our output. So that now what we've really shown is that all of our Fourier analysis that we've maybe done in the past, all of Fourier analysis is just, and if you'll humor me, I'm using just and trivial. That's just a trivial application of these eigenvalue, eigenvector applications or ideas or concepts that we've been using. So all of Fourier analysis is just a trivial result from expansion in eigenfunctions of this convolution operator or of an LTI operator. And one of the key points is that x of t and capital X of omega are really just different weightings of these eigenfunctions. Little x of t and capital X of omega are just different representations or expansions in different bases of this abstract signal x. Meaning you could look at x either in terms of its weightings x of t or its weightings capital X of omega. And we can see, maybe by looking at these integrals, what that really means. We now have these eigenfunctions, e to the I omega t, and now you can relate capital X of omega and X of t by this inner product relationship, which gives us all of this Fourier analysis. We will pick up at the next step of this. This was sort of motivating eigenfunctions, comparing it to eigenvalue and eigenvectors, and now you can maybe start to make the connection between finite dimensional and infinite dimensional spaces.